So I'm going to talk about today dwarf elliptical galaxies. So we have done a survey of these kind of galaxies in the Virgo cluster. So this is an image of 3 degrees by 3 degrees. So this is the core of the Virgo cluster. This is M87, that is the central galaxy. This is an image taken from the NGVS, the Next Generation Virgo Survey. The PI is Laura Ferrarese. And the galaxies that I am going to talk about are these dots here that the Virgo cluster is completely full about. And these galaxies are actually 10 to the 9 solar masses. So they are one magnitude above the dwarf spheroidals that we have been listening during the morning today. But still dwarfs, and you can see that they are very tiny things. So since the 80s, actually, we already knew that the number of dwarf elliptical galaxies were dominating in clusters, but they were very difficult or very rare in the local field. But this is the very recent work of Marla Jiha, where she has been trying to find quaint dwarf galaxies in the local universe, and actually the fraction of quaint galaxies for 10 to the 9 and below solar masses is 0. So they do not exist in isolation. Dwarf galaxies, dwarf quaint galaxies can only be found around more massive hosts or in clusters where dwarf ellipticals dominate by far. So these are just the typical values used to define dwarf ellipticals. So they are very the low luminosity and very low surface brightness galaxies. So we have conducted a survey of dwarf ellipticals in Virgo, and we got a spectroscopy for 39 DEs. This is the largest survey done so far. And you may be thinking, well, 39 is not that large, but well, you have to look at these galaxies one by one, because Virgo cluster is very sparse in the sky. So these galaxies are actually very separated from one to another, and they are very low surface brightness galaxies you have to integrate for very long hours. So you have to spend many years to collect only 39 DEs, and this is the largest survey done so far. So we have a spectroscopy for all these blue dots in this color magnitude diagram. So our dwarf ellipticals are a representative population of the early type galaxies in the Virgo cluster in this luminosity range. So these are just a few scaling relations to situate our galaxies with respect to the dwarf spheroidals that are these open symbols here, and with the massive ellipticals that are these triangles down there. So this is the mass-size relation, mass-velocity dispersion, and this is the fundamental plane. So this is the dwarf galaxies that I am going to talk about. This is my sample of 39 DEs. They are at 10 to the 9 solar masses. And they are in between the dwarf spheroidals and the massive ellipticals. So in our survey, we have conducted long-slit spectroscopy, so we can get resolved stellar kinematics for these dwarfs. And what we have found is that some DEs do not rotate, some others rotate mildly. So these are the first panel is the rotation curve, and the second panel is the velocity dispersion profile. And some other DEs rotate very fast. But we already knew that. So from the work of Marla Jiha in 2003, where she plotted the V over sigma versus the ellipticity, so this is quantifying the rotation over the velocity dispersion of the stars inside the galaxy versus the ellipticity, she already found that some DEs rotate very slowly or do not rotate, and some others were rotating. So this was a sample of 17 dwarf ellipticals in Virgo. So the next slides, in the next slides, I'm going to talk about things that we see in the rotation curves. So for that, you really need to trust your measurements and your uncertainties. And for that, I'm not going to go into the details, but I can explain this to you later. So we have done 3 independent tests to verify that. One test is internal. So the majority of our galaxies were observed with an instrument that has a dichroic and splits the light into a blue CCD and a red CCD with different gratings. So they are completely independent measurements. We can check if we get exactly the same answer with these two independent measurements of the same rotation curve. And we also compared our measurements with the galaxies in common with the work of Marla Jiha and the work of Igor Chilingarian. And everything was reliable, everything can be trusted, so then we go and analyze what is inside these rotation curves. So the first thing of all, we notice that we have two DEs that have something in the center that is behaving differently from the outer parts. So this is called a kinematically decoupled core, and it is believed to be a merger remnant. So these are dwarf mergers that as the ones that Alice was just describing, seen in dwarf elliptical galaxies in the Virgo cluster. So this has important implications because, as Alice was saying, dwarf mergers cannot happen inside dense environments. So this cannot happen inside the Virgo cluster. So these mergers must have happened when these galaxies were in the field, were still probably star forming before they went into the cluster. We have also made index diagrams, and we have seen that the kinematically decoupled core, this dark blue region in the center, is younger in both cases and slightly more metal rich than the outer parts or the main body of the galaxy. We have compared our numbers of kinematically decoupled cores versus the numbers of such features in massive ellipticals. We have compared with the Atlas 3D sample, that is a survey of 260 massive ellipticals in the local universe. This is a complete volume survey, and we have looked for KDCs not only in our Virgo DEs but also in the already published rotation curves, and we have found that the numbers actually are pretty similar. For the massive ellipticals, they also interpret the KDCs as the remnants of mergers, because they only find KDCs for the most massive ellipticals. Another thing that we find is that the rotation curves of the dwarf ellipticals can be very asymmetric. So that means that, for example, in this case, one side of the curve is not rotating, but the other it is rotating, or the rotation between the two sides is very different. One side is approaching towards us much faster than the receding side that is going away from us in the Doppler shift relation. So this is a kind of a weird feature, but now we are analyzing the same kind of asymmetries in the literature, and we are so they were there all along, but they were never reported before. So now we are quantifying that. And actually, if we plot where these asymmetries lie in the Virgo cluster, so this is just the Virgo cluster in the sky, in gray is all the early type population of galaxies in Virgo, and this is M87 in the center. These red dots are the galaxies that are smooth and symmetric. They have smooth and symmetric rotation curves, and these blue dots are the dwarf ellipticals with asymmetric rotation curves. So you can see that they tend to be in the center, the ones that are symmetric and smooth, and they tend to be in the outer parts, those that are completely asymmetric. So here I am plotting, this is basically the V over sigma relation versus the ellipticity. This is just the lambda or spin parameter that the team of Atlas 3D defined. So this line is what the Atlas 3D defined to be the line for slow rotators down here and the fast rotators up there, and all the gray dots are the massive ellipticals from that survey. So what we see here is that we have many slow rotators down here, and that was not necessarily expected. So in the Atlas 3D, they found that actually this plot is correlated with mass, and these are the most massive ellipticals, and the lowest massive ellipticals are up there. So finding so many dwarf ellipticals that are rotating so slowly was not necessarily expected. So as you can see here, this is the color code for this plot was this lambda parameter. So these red triangles here are the most massive ellipticals, that are the ones that are slowly rotating, and dwarf ellipticals are here, and this population here is here. So it looks like non-rotating ellipticals are either the most massive ones, or it has to be dwarf ellipticals. So what we were looking here is also two different symbols. We see these dots and these triangles here. So that is what I call the disk EDEs and the no disk EDEs. So I'm going to show you this to tell you about these things. So dwarf ellipticals can be split in normal or no disk EDEs, those are the ones that I am referring to, and the disk feature. So when you analyze the residuals of high filtered images, this is Sloan images, you see that some DEs actually have spiral arms, bars features, irregularities, and some others are completely smooth and normal. So what you see here is that the dots that are the no disk EDEs, the ones without any underlying feature, are down here and are rotating slowlier than those that have disky features that are rotating faster and up here. So this diagram also has different colors, and that is the distance to the center of the Virgo cluster. So red predominates here, that is the galaxies around M87. In orange, these are the ones here, are the DEs in the intermediate between 2 degrees and the virial radius of the cluster, and the orange one, the yellow ones are up here, that are the DEs beyond the virial radius of the cluster. So we have run different statistical tests, and we find always with a confidence level above 3 sigma that there is a correlation with the center of the cluster, so that the DEs in the center of the cluster rotate slowlier than those in the outer parts. So here I'm just zooming out of this image and adding here the stellar kinematics of spiral galaxies. So the spiral galaxies are above the dwarf ellipticals. So here I'm going to compare with the spiral galaxies of Adams et al. 2014. So these spiral galaxies are the blue stars, and you see that they have stellar masses in the range of our DEs. They have sizes that are also similar to our DEs. And here is the lambda that we saw already that they were above, but very interestingly, the velocity dispersion of that galaxies is already on the level of the dwarf ellipticals. So if you want to transform one of these spiral galaxies into a DE, you just have to decrease the rotation of the galaxy. They already have the mass and the velocity dispersion of the dwarf ellipticals. So just to conclude, we have done a survey of 39 DEs in the Virgo cluster. We have found 2 kinematically decoupled cores, which we believe are the remnants of major mergers between galaxies before entering the Virgo cluster. We have found that 33% of our galaxies have asymmetric rotation curves, and that these asymmetric rotation curves are for galaxies in the outer parts of the cluster. We have found 11 slow rotators, and within them 5 of them non-rotators. And we have found that the kinematic properties of these DEs correlate with the cluster-centric distance. So we find that DEs in the center of the Virgo cluster do not have any underlying structures. They have smooth and symmetric rotation curves, and they are rotating slowly or not rotating. And the DEs in the outer parts of the cluster, they have very strong rotation curves. They have underlying structures, and they have asymmetric rotation curves. So what we think that we are looking at is the settling of the DEs in the Virgo cluster. So it's actually a great opportunity to understand the physical processes that are transforming these galaxies in the cluster. So as a summary, what we think is that what we are looking at is at the different stages of the dwarf ellipticals in their transformation since they were in the field and start forming towards the center of the cluster. That's all. Thank you.
Thank you very much. So questions, always the same people. And maybe we can start with you. No? Oh, wait a minute. Come on! It's a good one. I know. Yeah, no.
Question about the time scale of this transformation. From the number counts, could you infer some bounds of how fast this might be?
I think that's a very interesting question, but we haven't looked into that yet. And I don't know what kind of parameters, because probably you will need the orbital properties of some of the galaxies to know how fast they are coming in, or yeah. So we haven't looked into that. Yeah.
All right. So this is a really nice map of how galaxies kind of lose their gas and then start getting beaten up by the cluster potential, which is really cool. The things I'm really struggling to understand are the kinematically decoupled cores. And so I guess I have two questions, although there's really one big one. Is presumably you should see this also in dwarf irregulars in the field. If it is a merger signature, fine, then you'd expect to see the same thing in dwarf irregulars in the field. It may just be that it's too hard to measure because people do H1, H alpha in the field, and they never bother looking at stars because they're, pain in the butt. So do you know of any literature about that? And then I guess the follow-on question is, if you did, because these guys fell into a cluster, let's say at redshift 1, just for the sake of argument. And so they had all the late gas accretion shut off. And so I'm wondering, even if there weren't any kinematically decoupled cores in dwarf irregulars, it may just be that they're all regrowing a disk after a merger. So I'm just kind of wondering, what are your thoughts about these KDCs? They're really fascinating.
I didn't understand the second question.
Well, let's do the first thing.
Okay, so
dwarf irregulars, are there any that you know of?
So there are only 2 papers looking at the stellar kinematics of low luminosity star-forming galaxies, and they don't find any kinematically decoupled cores. But one is based on 7, so that's the ones I was comparing to, and the other is only 4. So probably it's low numbers yet to find. So we found 2 in a sample of 39. So if they have 4 only, so probably it's just they didn't get lucky. Yeah. So the second question was about the.
Okay, we'll talk about it later.
Okay.
You had also a question on the back.
Oh yeah, absolutely. Yeah, but you cannot. Yeah, exactly. So that's the problem. Yes. Yeah, but if it is there in projection, then it should be even better if you the project, right? Yeah.
I was just going to say, just following up on this, that when the engineers are trying to do stuff with restorations to get line of sight distances for the purposes of something that is probably not, those distances are not precise enough. It's worth looking that people are getting better and better
Yeah.
SPF distances.
Okay. David, yeah. We are already in the discussion part. We have 50 minutes of discussion, so why not discussing it right away? Because otherwise we forget. I forget.
Okay.
Are you able to determine the metallicities? Do you see some additional signature of what might be unusual in the different subclasses of your?
So we have measured the metallicities, but we have done it with Lick spectral indices so far. So the error bars are quite large. But the metallicities are all subsolar. So they are slightly more metal rich than the dwarf spheroidals that are at around -1.5. So these are like between -1.2 and -0.5, something like that. But it doesn't correlate, for example, with the cluster-centric distance, and it doesn't correlate if they are disky or no disky DEs. So, but we don't know if we try to, so the idea is to try to measure this with Charlie's model, with Charlie Conry's models, to try to improve the error bars and see if when you have a cleaner measurement, you can do something with that. Yeah.
What about the metallicity gradient? I guess I should ask.
Oh, the metallicity gradient is very tough because yeah, you need a very high signal to noise, and yeah, so I don't know about that yet. Yeah.
Just one more point about cluster-centric radius. Something like Virgo is so lumpy and where there are subclumps within it. It's not clear that cluster-centric radius is the best measure of the local environment of a galaxy. I know Elisa, you've looked into this. That maybe the distance from the nearest big galaxy might be a better metric.
Yep. What here? Okay,
So I'm actually confused by the statement about the cluster-centric distance. I was distracted when you showed the plot. But are you talking about constant stellar mass, or what you're reporting is just a trend that actually is driven by stellar mass? Do you see a change in the rotational support of galaxies going towards the cluster center at constant stellar mass, or are you saying that the galaxies that you have in the center of the cluster are more massive than the galaxies that you have in the outskirts of the cluster?
No, these are all for 10 to the 9 solar masses. So this is at a constant stellar mass. And if you go to higher mass, to the more massive galaxies, 10 to the 10 to 10 to the 12, then there is no correlation with the cluster centric distance. But because these galaxies are dwarfs, so they are very easily perturbed by the environment. But when you go to a more massive galaxy, then the potential is too high to destroy the galaxy, then it's not that easy.
This is at 10 to the 9.
But this is that's constant, yes, stellar mass. Yeah.
Yeah, so thank you very much.
Thank you. Galaxies that I am going to talk about are these dots here that the Virgo cluster is completely full about. And these galaxies are actually 10 to the 9 solar masses. So they are one magnitude above the dwarf spheroidals that we have been listening during the morning today. But still dwarfs, and you can see that they are very tiny things. So since the 80s, actually, we already knew that the number of dwarf elliptical galaxies were dominating in clusters, but they were very difficult or very rare. So I'm going to talk about today dwarf elliptical galaxies. So we have done a survey of these kind of galaxies in the Virgo cluster. So this is an image of 3 degrees by 3 degrees. So this is the core of the Virgo cluster. This is M87, that is the central galaxy. This is an image taken from the NGVS, the Next Generation Virgo Survey. The PI is Laura Ferrarese. And to define dwarf elliptical, so they are very the low luminosity and very low surface brightness galaxies. So we have conducted a survey of dwarf ellipticals in Virgo, and we got a spectroscopy for 39 DEs. This is the largest survey done so far. And you may be thinking, well, 39 is not that large, but well, you have to look at these galaxies one by one, because Virgo cluster is very sparse in the sky. So these galaxies are actually very separated from one to another, and they are very low surface brightness galaxies. You have to integrate for very long hours. So you have to spend many years to collect only 39 DEs, and this is the largest survey done so far. So we have a spectroscopy for all these blue dots in this color magnitude diagram. So our dwarf ellipticals are a representative population of the early type galaxies in the Virgo cluster in this luminosity range. So these are just a few scaling relations to situate our galaxies with respect to the dwarf spheroidals that are this over in the local field. But this is the very recent work of Marla Jiha, where she has been trying to find quaint dwarf galaxies in the local universe, and actually the fraction of quench galaxies for 10 to the 9 and below solar masses is 0. So they do not exist in isolation. Dwarf galaxies, dwarf quench galaxies can only be found around more massive hosts or in clusters where dwarf ellipticals dominate by far. So these are just the typical values used to